too true, I know it's there.
Okay, I gotta start it up. Hopefully the microphone's working. Like to get through about 70 to 80 slides today to keep us on track. We might be probably a section or a half section behind. That's not gonna be the end of the world. We kind of have that built in. I normally go over a little bit. So this is the last section talking about repeaters. Like last week, I couldn't see ahead. What's up with Nicholas? We could have just gone more slides with the section, but this is the last of the questions here. And it's asking you, when transmitting phone signals, how do you have to do that? Does it have to be in purely phone, or can it be in something else? And the answer to that, when transmitting phone, you can either transmit phone or Morse code your call sign. So, just on the right. So, our repeater will transmit Morse code to identify itself. That's totally legal, even though it does transmit phone. Which of the following describes a simple dipole oriented parallel to the Earth's surface? So, really quickly, the most basic antenna we're going to be covering in this is the dipole. A dipole, usually we're doing a half wavelength dipole, quarter wavelength on each end, is represented like this, with where the ground orientation is here. This is the ground, and it's fed like this. So this is a dipole, so horizontally to the ground, and this length here is lambda over 4, and this total length is lambda over 2. It's the most basic antenna we're going to talk about. We'll also cover briefly a monopole, which is just an antenna like this, where this is lambda over 4. What else do you use? We'll talk really quickly about 5/8 wavelengths. But we have an antenna like this. It electrically looks like a lambda over 2 antenna because of reflections from the ground. So those are dipoles.
Where does a fork come from? What is that?
The fork?
The four.
The four?
Yeah, lambda over 4?
Lambda over 4, that's just electrically how long it is. Lambda is the wavelength of what frequency would be going through the dipole. So if we want to tune your dipole, how long is your dipole? So that is the length of the dipole, where lambda is the wavelength of the frequency you're using, divided by 4.
Why is it always 4?
I mean, I could write out the nasty math.
No, I just that number 4 coming up. Who's number 4?
I could write out the nasty math, but no one would like me. It's got a lot of integrals in it.
Got a lot of
So
folks in here too. So,
it just mostly has to do with how the wave can propagate through that and how it propagates to a vacuum between that. But I won't prove it to you.
that's an antenna like this with a kind of like things like that. Is that what we're talking about? Like this? It has a loop like this, and that's a direction.
This is literally what the antenna looks like. So it's fed here with an oscillator, whatever your frequency is. Goes off on one end, it goes off on the other end. It's a wire antenna.
That's just a big long.
Yep.
big long wire like they're going on.
Yep. That is a dipole antenna.
Wonder what that water source was. Got a hell of a way behind closed.
So this is answer B, which is a horizontally polarized antenna. That makes sense. Horizontally polarized. Or it's a linearly polarized antenna, means it's not circularly polarized, but it's horizontal to the earth. So
Well, that's what a TV antenna is. Little ones like that.
most TVs are circularly polarized antennas, but we won't circularly polarized. We're not going to go into that. Asking the antenna questions can be dangerous, so I don't want to confuse you. And which of the following, which direction does a half-wave dipole antenna radiate the strongest signal? So from this depiction I have up here on the board, does anyone know which answer it is? It should be C, which is broadside of the antenna, so it transmits out like this and not like this. So it's a radiation pattern in space. Looks like this, where this is the null out here. Kind of like, more like a figure 8. Like one of the questions, and I'm not sure because I haven't checked over this since the question change here, is it'll ask you what happens as we move this dipole closer to the ground. What happens is its radiation pattern becomes more omnidirectional. The reflections cause this to be more circularly radiation. So that's a question too, just based on it. So it transmits better in all directions. The closer you are to the ground, it has more directionality, more gain in direction, the farther it is up from the ground. Very simple antenna theory here. So that's the broad side of the antenna. Okay, now we've got to do a little bit of math. Like I said, it's not hard math. This is, we'll do some decimal stuff, but I can teach you some tricks. What is the approximate length in inches of a half wavelength 6-meter dipole antenna? So for this, we got to think we've got a half wavelength, so that tells you exactly what it is. First thing you need to know is 6 meters divided by 2 is 3 meters. So we have about 3 meters. We can, with our head, say about 3 meters is approximately how many feet? About 9 feet-ish. It's a little bit more. Or, yeah, just short of 10, but 9 feet works good enough to get it. We've got pretty big drastic changes in the numbers here, so we can get a pretty good approximation here. So we convert 9 feet, we got 12 inches. Feet, how many is that there? It's probably C. C is probably the closest. Yeah, answer is 123. You can do the approximate. I can that approximation I did there is 100% valid for any of the questions here. If you want to learn the more specific one, you can, but this is easier to memorize. So that's how I teach it. Ballpark everything. You don't have to be very accurate with your approximations. When you make antennas, and I hope he walks by as I say this, the person who's proctoring the exams today, Brad, made a dipole during last year's November sweepstakes, which is a contest we do every November. He made a dipole for 80 meters, and he used a similar approximation. Antennas don't like that kind of approximation, and the antenna was about 6 or 7 feet short of what it should have been using that approximation, and it didn't work very well. It's a lot harder to add length to a very long piece of copper than it is to take away. So we still give them a hard time for that. So don't use the approximation when you're making an antenna. There's lots of good calculators to give you very specifics on how long your antenna should be exactly, and you can take into factor a few more other things, but that is a good approximation for making a dipole. How would you change a dipole to make it resonant on a higher frequency? So if you have frequency and wavelength are inversely proportional, so if you have a higher frequency, if you have a high frequency wave, it's going to have a smaller wavelength. So you are going to want to shorten your antenna. What is the approximate length in inches of a quarter wavelength vertical antenna? So that's the one I drew over here on 146 megahertz. So now you've got to do two things. You've got to figure out what 146 megahertz is in wavelength. I told you the approximation here would be lambda equals C, which we use 300 for, so we don't need to memorize that because we're doing in megahertz. 300, and we got 146, which rounds pretty well to 150. That would be 2 meters. So that's 2 meter So now we're going to take 1/4 of 2 meters. Let's convert meters to feet. Meters to feet is about what? About
12.5.
something like that. So we can know from that we're about 19 inches is a quarter wavelength. So those approximations you can do in your head work perfectly fine. You can do exact calculations when you need to, but especially when we're dealing with electromagnetic stuff and propagating waves, we like to think about things in wavelength a lot. I'm taking an EMC course this semester. We got to kind of have that in the back of our head all the time. We got to know what wavelength and frequency, how they relate to each other. We can think of everything in terms of wavelength. So if I sit there and take out my calculator every time, or even do an exact approximation in my head, it'll slow me down. I want to know exactly. I want to know a ballpark answer pretty quickly. So that's the way I like to teach it. If you want to do the more the more exact one, I mean, I would definitely do that if you're making an antenna. What type of antenna are quad, Yagi, and dish antennas? They're all directional antennas. A Yagi antenna, you can see on top of our tower over there. It's missing a few elements. We're going to get a new Yagis pretty soon here. They're ordered and they're sitting in boxes in the radio room. But those are all very directional antennas. Very quickly, I like to talk about Yagis because they're cool. I'm going to try to draw three-dimensional space here. So right here, I've got a gap where I'm feeding this. Right here. This is your driven element. All of these other elements in a Yagi antenna are passive. And the way they work is using destructive interference and what's the inverse of that? Yes. You get a very directional pattern. But if you were to look at this part on a traditional Yagi, a Yagi that is one band, the ones we use have multiple bands, they have traps and stuff. This is going to be a dipole right here. So this is your driven element. You have directors and reflectors. Reflectors are back there, directors are there. They get smaller and smaller as you go out. The more you have, the more you can do the complications and how the array works and how they reflect with each other. You can do fancy math here with how far they should be separated. But that's all you need to know is, I don't need to know for the exam anymore.
Receiver antenna?
All antennas transmit and receive.
Okay, but it's coming in one way, it's going to be reversed from the other way, right? You got the dipole, you said it's directional, so you're speeding out this way, it's directional.
So
it's coming this way, what's happening?
So if you have an antenna that's directional, it's going to, in three-dimensional space, it's going to say if I have a directional antenna that likes to pick up something in a pattern right here, I can draw like kind of like a circle here. We can kind of think about this in northeast west. So we've got this, we've got an antenna that's directional like this, where its gain is like this. It will pick up and receive anything on these angles. And then it's got nulls, and it usually has some back ones here where it transmits. That has to do with the math of the antenna and how it works. And every antenna, it's based on their geometry, and it's based on mostly geometry and current distribution is how it works. But this is how an antenna works. It receives and transmits. It does both. It does both within the same math. So beam antenna, that's an antenna that concentrates signals in one direction or one direction better than others. It has gain in a certain direction. So the gain this way is where we would talk about it. So if I told you the gain of this antenna was 50 dB, pretty pretty high. That would be referring to this part right here, the highest part of the antenna. Using a directional antenna, how might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of path? The answer there is try to find a path that reflects the signal to the repeater. Especially on VHF, VHF loves to interact with walls and buildings. You can get a pretty good reflection off of those. So even if you have something completely in your way, you can usually get a reflection somewhere. That makes doing fox hunts or hidden transmitter type stuff more difficult to do because you get reflections. Which of the following methods is used to locate sources of noise, interference, or jamming? Let's see, radio directional finding. We've been talking about that before and after class. That's our senior design project this semester. Me and a few other radio club people. So, and then you guys are using it for a few other things as well. So, which of these items would be useful for a hidden transmitter hunt? Calibrated SWR meter, a directional antenna, a calibrated noise bridge. That would be a directional antenna, would be something that is useful. Traditional method of finding a hidden transmitter or a source of interference is take a radio receiver that can show you signal strength and have an antenna that's directional, and based off of going and taking a few points when it's transmitting, you can figure out the general direction. You got to take into account things are going to bounce off of stuff. This is something that happens to us quite often when we do fox hunts, is the signal can be so strong and be reflected from so many different things. No matter where you go, your radio is giving you full strength. So there's ways to deal with that as well. You can take your signal and attenuate it. One I like to tell people is take your radio receiver and take it off frequency just a little bit. So you get part of the FM. Take it 5 kilohertz off, that attenuates your signal. You can then see where it's coming from easier. What is the gain of the antenna? Just said it. Have to read. Answer C is the gain of the antenna. It's the increase in signal strength in a specific direction compared to a reference antenna. I didn't really talk about that. We use a few different things for reference antennas. Industry standard for a reference antenna is an isotropic antenna. Isotropic antennas don't exist, but they are antennas that transmit equally in all directions. Those don't exist, but that is industry standard. A dipole is also used sometimes if you read the gain of an antenna. You can get higher gain if you reference it to a dipole than an isotropic antenna. That's not industry standard. We always use isotropic antennas. What antenna polarization is normally used for long distance weak signal CW and single sideband contacts using the VHF and UHF bands? Okay, so you have what I described as horizontal. We also have vertical polarization. Vertical polarization is most used within FM contacts on VHF and UHF. When we start talking, and this is kind of more something practical to think about, is if you have an 80 meter dipole, you guys don't have privileges as technicians on 80 meters, but the generals and extras do. If you have an 80 meter antenna, that's a really, really long dipole. Getting it up like that means you're going to have to probably have a tower. Or you can string it up between 2 trees. So, generally speaking, when we're using weak signal propagation, which is done on the HF, we use horizontal polarization instead of vertical. Vertical is used a lot in FM, especially in the amateur radio bands. So that with weak signal propagation carries over even on the VHF and UHF. So we do use horizontal for that. Does that make sense? Drink of water. What can happen if the antenna at opposite ends of a VHF and UHF line of line of sight links are not using the same polarization? Signals could be significantly weaker. It's absolutely true. And they says it can go as much as 100 times. That is completely correct. If you have polarizations in the opposite, you get about 10 dB difference. So something to consider is making sure you have the same polarization when talking between friends. What is the advantage of using a properly mounted 5/8 wavelength antenna for VHF and UHF mobile service? So this has a very similar antenna pattern to a dipole, this quarter wavelength dipole, where it transmits pretty well in all directions. A 5/8 is different than that. It takes some of its power and it directs it at lower angles. You've got this antenna, it's going to kind of transmit this heart kind of shape here. You'll have a little bit of a null right here, but you're losing power upwards. You don't want to transmit power upwards if you're talking ground to ground. So what we can do with the 5/8 wave antenna is it kind of takes that and it narrows it down, puts the gain kind of in this direction where it's going outward more. So that's what a 5/8 wave antenna does. Which of the following describes an antenna loading? Answer A, inserting an inductor in the radiation portion of the antenna to make it electrically longer. We do this a lot, especially rubber ducks are the best example of that. And I think I have my radio in my backpack today, so I can show you my severely damaged rubber duck antenna. We were doing a fox hunt. It's in here somewhere. Here's my severely damaged rubber duck antenna. But I'll pass it around. You can see there's a coil in there. That's a big inductor. I love those antennas.
Yes, yours is damaged.
I break everything. This is supposed to be an invincible radio. The screen is cracked. All the rubber's falling off. I've had it for a while, but I carry it with me every day.
It's just a coil.
That's a coil or inductor.
Okay.
We'll talk about that a little bit more.
So if you were to stretch this out, it would.
Yes and no. It wouldn't be the same length of 5/8 wave antenna necessarily.
If you did it like this, is that? What do you say,
It's
something like this and pushing it in smaller?
It's more complicated than that. You get a magnetic field that goes around with it. So magnetic field is different than it is just other. So it makes it electrically longer. That math might not transfer perfectly over to how many turns it has.
Okay.
So if I was to stretch this out, it may not be perfectly 5/8 wavelength, but it does make it electrically longer.
Okay. So instead of a big long one, you can wrap it around there and have a small.
Yes, and there's math associated with that.
And that's called an inductor.
That's a rubber ducky antenna, but you get an inductor.
The coil part.
Inductor. You can. I'll forget it.
Very coil, very wide. That is actually a metal inside there, like copper or something?
That's all copper. It's all copper. Probably all the same wire too. You could probably stretch it out and it'd be one long antenna. It might necessarily not be 5/8 wave. This is a 5/8 wave antenna, by the way. I need to buy a new one. I've been saying I was going to for a while. I've had it for a while. Okay, we're going to start talking about emergencies. So that is all you need to know about antennas. It's not very difficult. You know that there's something called a radiation pattern. You know antennas have gain, but you don't have to look at it. Do they amateur general, the amateur extra? You might have to look at those things. You might have to look at a chart and say the gain is this, half power beam width is this. But for the purposes of the technician, you don't have to go in much more detail than that. Which of the following is an accepted practice to get the immediate attention of a net control station when reporting an emergency? You can see it. You can say priority or emergency. Some people say break. Those are all things that will tell people that you need to have priority when talking on a net. A net, for people who don't know, is a time that amateurs will get on. It's either that they'll run nets when we're running operations like a race, or we'll run it for fun, just kind of a net to talk. But a net, because you're transmitting on one frequency usually, has a net control who organizes how the flow of the communications go. The net control will open said net, call for check-ins to net, and then call on individuals, whether they have traffic to report or they want to just talk. We have a net we run weekly where we just have people get on there and they talk. We sometimes give them a subject, but it's practice for people to get on here. Which of the following is an accepted practice for an amateur operator who has checked into a net? Answer C, remain on the frequency without transmitting until asked to do so by the net control station. When do the FCC rules not apply for operating on an amateur station? D, they always apply. Which of the following describes the Radio Amateur Civil Emergency Service, or RACES? Let's answer D. It's a radio service using amateur frequencies for emergency management of civil defense communication. Radio service for using amateur stations for emergency management of civil defense communications and emergency service using amateur operators certified by a civil defense organization as being enrolled in that organization. That's a mouthful. There's lots of ways to get involved in RACES. There's also another organization called ARES. They'll talk about that, but they both have to do with emergency services. Here's ARES. So ARES is a licensed amateurs who volunteer register their qualifications and equipment for communication duty and public service. They do exercises a lot. You'll hear them have nets where they practice passing communications for disasters. A lot of times ARES and Saturn, which is the Salvation Army Amateur Radio organization, will have an emergency communication setup of some sort to deploy during emergencies. I know in Kansas City, the Saturn band also is used by ARES. They have that ready to deploy. They deployed it in Joplin to have emergency communications for volunteers down in Joplin and when the cell phones were there. So it's a cool band. They've got lots of radios in there, and they were able to set up pretty good communications network pretty quickly. What do RACES and ARES have in common? They help provide communications during emergencies. Are amateur station control operators ever permitted to operate outside the frequency privileges of their license class? That answer is D, yes, but only necessary when involving immediate safety of human life or protection of property. So earlier they said, can you ever break the rules? And they were like, no, you always have to break the rules. It's part of the rules. You still have to operate as an amateur would in all situations, but if you need to transmit on a frequency that's not yours, it's got to be life and death. What is meant by the term NCS used in net operation? That's answer B, net control station, NCS. What does the term traffic refer to in net operation? That is answer A, formal messages exchanged by net stations. What information is contained in the preamble of a formal traffic message? So formal traffic messages are sent very, very, very rarely. Radio telegraph is what this is kind of referring to. But they're also used in emergency coordination stuff as well. But it has the information, I believe it's answer D, the information needed to track the message. Which of the following is a characteristic of good traffic handling? All of these things are correct. Oh, no, it's not. Sorry. Passing message exactly as received. Last year was all of these were correct. But you want to make sure that you don't change anything. They do counts, word counts, letter counts on things as well to make sure that everything is checked correctly. I don't know if that's still a question. Yep. What should be done when using voice modes to ensure that voice messages contain unusual words are received correctly? You can spell out words using the standard phonetic alphabet. What is meant by the term check? Just said that. To answer A, the number of words or word equivalents in text portion of the message. Okay, now we're going to get to some of my favorite stuff, which is weak signal propagation. I'm going to talk a little bit about modes associated with that. Why do VHF and UHF radio signals usually travel somewhat farther than the visual line of sight distance between two stations? That is, the Earth seems less curved to radio waves than light, and that has to do with their wavelength. What might the range of VHF and UHF signals be greater in the winter? I think that's a new question. Less absorption of vegetation. Vegetation leaves to pick up a lot of things. Also transmit noise, but when you're able to see further, you're able to transmit further. So that's a good question. I like that one. That's new.
Is that a new one?
That is 100% a new one. It was new, at least between the last set. But I've never heard it. How may fog and light rain affect radio range on the 10 meter and 6 meter bands? Fog and light rain will have little effect on these bands. It doesn't really, the wavelengths don't really interact much with fog and rain. There are frequencies in which that does happen, but those are not them. Why are direct, not via repeater, UHF signals rarely heard from stations outside your local coverage area? Answer C. UHF signals are not usually reflected by the ionosphere. We talked about the ionosphere, and we'll have a graph up here in a second. If I draw it, I'll draw it backwards. It happens every time, and I can never get it straight. And we'll talk about the layers here of the ionosphere. But generally speaking, HF frequencies, high frequencies from 3 megahertz to 30 megahertz get reflected, and portions of the VHF band you get bounced off the ionosphere in some special conditions. But for the most part, well, for definitely the UHF signals don't, but mostly it's just HF that does. Which of the following, can't read the question, might cause radio signals to be heard despite obstructions between the transmitter and receiver stations? That's knife edge diffraction. If you have a transmitter and it's transmitting this way, you've got a sharp peak here, the radio wave will bounce over sharp peaks. They don't like to interact with sharp things. What mode is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? That is tropospheric ducting. That has to do with temperature inversions in the atmosphere. Radio waves will get stuck in between them and they'll keep bouncing around and going down. Basic how it works, but doesn't have to do with the D layer, the F2, has to do with temperature inversions or tropospheric ducting. Causes tropospheric ducting, temperature inversions in the atmosphere. What weather conditions would decrease range at a microwave frequencies? The answer is water. So that definitely, you get closer to kind of the resonant frequency of water, you're gonna have some issues when it rains. Microwaves are closer to the frequency of that. Those smaller particles, you're talking about wavelengths in the centimeter range when we're talking about the wavelength of microwaves.
Microwave is centimeter.
Yeah, about the centimeter, yeah. Centimeter range is where it kind of starts. One of the first bands in the UHF, which is partially microwave, we can call UHF microwave, is 70 centimeters, and it goes all the way down. So I work in a microwave lab, so we all deal in centimeters up to millimeter waves. Very small. As compared to an 80-meter wavelength, that's huge. What is the characteristic of a VHF signal received via aurora reflection? Kind of scatters it, makes it fluttery sounding. Answer B, the signal rapid fluctuations of strength and often sound distorted.
So what does that sound like?
What was that?
What would that sound like? So the sound fluttered.
There's a great audio clip.
2 meter will reflect on aurora curtains.
It's aurora reflection, so like the aurora borealis. You got the part of the magnetosphere of the Earth. You can bounce off of that. Those strong electromagnetic anomalies. Yeah. Yeah. And we have a lot of sun activity, a lot of aurora activity, and then you can mess with your antennas. What band is best suited for communications via meteor scatter? That's 6 meters. There's 2 major meteor scatters. Can't remember them off the top of my head. Perseus and the, what's the other one? I can't think. Yeah. We just recently had it too. Yeah. They have them twice a year. People like to, you can do radio bounce off of those. Works pretty well.
Just wait till it's meteorite showers.
Yeah, you can get propagation off of them. There's the ionospheric layers. Every year I tried to draw this, and I finally just kept this slide in, so I didn't embarrass myself with getting the layers in incorrect order.
Where is the ionosphere?
The ionosphere is anything from the most inner layer, which is the D layer, all the way to the F2. So it starts anywhere from 25 miles and goes up the way to 250 miles. So it's pretty long. So charged particles in the atmosphere is what we're referring to when we're talking about the ionosphere.
So during the daytime, the atmosphere heats up, so it expands outward, right?
You get solar charge, yes. So different layers. This is a good illustration. You get different layers that are more active based on if they're charged or not. So
I assume that this is like a peeling on an onion. This is a circle around it. There's no holes in it, is there?
If you're talking about, if you have a frequency of like 30 megahertz, it may not interact the same as a frequency at 3 megahertz. So different frequencies interact differently with the ionosphere. And different frequencies interact with different layers of the ionosphere.
So the ionosphere, what meter length are we talking about for the ionosphere?
So you'll get ionospheric bounce, and it depends what kind of ionospheric bounce you get for which frequency, but you'll get ionospheric bounce anyway in the HF spectrum for the most part. So 3 megahertz to 30 megahertz is really where that mostly happens. There is some exceptions to that. It does go into the VHF a little bit, but it's 3 megahertz to 30 megahertz. So as far as if you want a bird's eye view, this is not the complete side of how things work. You get the lower frequencies tend to work better if we're talking, we'll say like full break. We'll have 3 megahertz, which are pretty low frequency in the HF, kind of on the edge. The 80 meter, the 160 meter band, the 160 meter bands even lower than that. But the 80 meters, they tend to work better at night. 40 meters, well, I'll just refer to them in their wavelength, so it's easier for me to think about. 80 meters and 40 meter, 160, 80, and 40 are kind of considered your night. This is maybe an evening band, 40. And then your daytime bands, maybe your evening, 20 meter, we have more of an evening. It works all the day, but it works well into the evening. There's 20 meters. I can make denotions here. This is 7 megahertz. This is all 14 megahertz. And you have 10 meters. 10 meters needs some more special conditions to open. When it does open, it opens very well. 10 meters means usually the propagation, the best propagation I've ever had is on 10 meters. It's based on the solar activity. So when we're peak sunspot activity, which happens on a cycle, it was probably about 5 years ago. We were kind of at the end of our peak. When I got my license, I could hear myself. I bounced from here all the way around and back to myself. I had the delay of speed of light where I could hear myself. Weaker, but I could hear myself. That happened on 10 meters. 10 meters works really well when it's there, but it doesn't happen very often. So it's kind of the money band when it's open, but when it's not, it's just kind of dead. 20 meters tends to be open pretty much all the time. It does have to do with how the sunspot activity is, and there's certain magnetic storms that'll wipe them out, make it too noisy. But you want it to be a mirror for the frequencies. Sometimes it'll get too active and it'll be not a mirror.
So that's when you're shortwave radio day and night. You keep turning around to get the best one. That's because of the reflection of the ions.
Yes.
Okay.
Yes. Which part of the atmosphere enables the propagation of radio signals around the world? That is the ionosphere. On which HF bands does a technician class operator have phone privileges? That is the 10 meter band only. This 10 meter band doesn't open, like I said, all that often, but when it does, it opens up well. That's 28 megahertz, if you're curious of frequency. I think that you have to know that to know what your privileges are. Question. I did not read the question. Which of the following is an advantage of HF versus VHF and higher frequencies? Long distance ionosphere propagation is far more common on HF. It happens a lot more. There is things like tropospheric ducting, and 6 meters has some sporadic E that opens up that works. But as far as long distance communications go, radio to radio long distance communication without a repeater, HF is the way to go. Which of the following HF bands have frequencies available to technician class operators for RTTY, RTTY, and data transmissions? I'm not super happy that they're making you memorize this because I don't know why it applies. I guess it's technicians, so it does apply to you guys, but most people don't use these. I believe this is going to be a memorization question. I can tell you that the 17 meter band has quite a bit of limitations on it, and the 30 meter band has quite a bit of limitations on it. So I can narrow it down before I've seen this question to one of the two, which is either the 10 meter or the 10 to 15 to 40 and 80, and that's probably my guess, but I may be wrong. Nope, it's the D, so I was wrong. So it is only the 10 meter band that you have those privileges on for RTTY that's very similar to phone. I know they do allow CW.
I heard there's a test session.
So the test session is in 102.
Okay.
So we got two things going on right now for Ham Radio Club, but
All right, cool. Yep, thanks.
Brad should be in there.
So, an example of data transmission, what would that be?
It's opposed to using a phone signal or a Morse code signal. We can transmit data. There's a lot of different ways to do that. There are a lot of different methods to do it. We can transmit data packets, ones and zeros, via frequency. There's a lot of different ways to do it. We can do it with frequency shifting. We can do it with phase shifting. But what it's saying is there are data modes, and they are only on 10 meter for technician.
Okay.
You can transmit those when you get to general and extra on different frequencies. So 10 meter band is the only place to do that. What is the FCC Part 97 definition of a beacon? Answer C, an amateur station transmitting communications for the purposes of observing propagation or related to experimental activities. So you can have a beacon on a frequency to listen to hear the propagation. That happens a lot. People know that there's a beacon here, and if you can hear it, it means the propagation's good on this band. A lot of 10 meter beacons to figure out when 10 meters is open. There are other bands as well. And you can look them up too. Usually they just transmit Morse. Another good way to listen to see if the bands are open is you can listen to shortwave radio as well, but that's not everywhere. What is generally the best, don't do that. Best time for long distance 10 meter band propagation via the F layer? The F layer, shortly after sunset during periods of high sunspot activity. So we don't have a ton of sunspot activity right now. Don't like this question because you don't have a ton of things that work you get to use for the F layer unless you're on Morse code. So I really wish they would. Almost shortly after sunset. Okay, it does happen on 10 meters. So that you got sunset, kind of a good time for a lot of bands too. Something to think about. Misread that question. Which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? So we talked about polarization earlier. If you get skip signals from the ionosphere, it really doesn't matter if you have horizontal or vertical polarization. For the most part, most people are using horizontal polarization, but vertical is a good way to go to. You can use that, but it doesn't matter as much because when it comes down off the ionosphere, it's elliptically polarized. And that just has to do with how it interacts. Which of the following propagation types are most commonly associated with the occasional strong over-the-horizon signals on 10, 6, and 2? That's sporadic E. Which of the following bands may provide long-distance communications during the peak of the sunspot cycle? That is 6 and 10. But we are not in the peak of the sunspot activity. You'll have to wait, I think, a few more years before we get back into that. What property of radio waves is used to describe its polarization? It's electric field. Which of the following is likely cause of irregularly fading of signals received by atmospheric reflection? That is answer C, interference from thunderstorm. No, sorry, that's answer B. Random combining of signals arriving via different paths. That happens a lot. You'll get, especially when the propagation is very good. It's mostly just you'll come off different paths of the ionosphere. You can even have it come via long and short path. So there's times where you'll be talking to someone almost on the other side of the planet where you're hearing him multipath. So you'll have almost an echo in the transmission. Satellites. What is the Part 97 definition of a space station? That's answer C, an amateur station located more than 50 kilometers above the Earth's surface. Which of the following radio stations may make contact with an amateur radio station on the International Space Station using a 2 meter and 70 centimeter frequencies? Anyone with a technician or a higher class? It's where you can transmit. Do the initials LEO stand for an amateur satellite? That's a low Earth orbit. There's some basic, I think they don't ask a ton about different orbits in here. Which of the following are provided by satellite tracking programs? Time, azimuth, and elevation, start and maximum altitude, and the path, I believe. Oh, no, all of them. Doppler shift as well. Maps showing the real-time position of satellite track over the Earth. Which of the following are inputs to a satellite tracking program? It's the Keplerian elements. Satellite beacon, Keplerian elements are just Keplerian element properly. They just have to do with where it is. It's where it is relative to your. What is a satellite beacon? It's like a beacon, but it's space. So a transmission from a satellite contains status information about the satellite. What mode of transmission is commonly used by an amateur radio satellites? Single side. I think the answer is all choices are correct. That's probably, it's not really correct. I'll tell you that most of them are FM and data. CW is not a thing as much anymore in single sideband. I don't think there are any satellites currently that operate on single sideband, but they're going to say, answer D, all of these are correct. You can do all that, but that's not common. Who may receive telemetry from a space station? Anyone who can receive it. Don't have to have a license to receive its frequency. What telemetry information is typically transmitted by satellite beacons? So answer C, health and status of the satellite. What causes spin fading on a satellite signals? Yep. So you've got the gain. All antennas are going to have a little bit of gain to them. You're not going to have perfectly isotropic antennas. So as they shift, you're going to get weaker and stronger signals. With regarding to satellite communication, what is Doppler shift? That is answer C, a mode where the satellite receives signals on one band. I say it's not. I feel like this isn't correct. I don't want to look that question up. It's like the question is wrong for the answers. Is it a duplicate? I didn't make these, so I can't take credit for that.
Yeah, I think it might be the same way. I ran across some of those in the phone application.
Oh, really? And I note that sometimes they do have errors and they'll scratch questions. So this may be one of those where they release something with a correct. That is not what Doppler shift is.
Doppler effect, it's coming, going away from
It's
receding, it will change the frequency.
Yes. Yeah, that's what Doppler is. This is not correct. I'm glad we at least caught that. What this is talking about is UV split. That's what the answer is for that. But the question and the answers do not match. I think it's a mistake on their part. I'll have to look that up. Maybe they've scratched this question from the question pool. Or it's either that or it was inserted wrong into the slide.
The answer at the bottom is correct.
Yeah, but where's it?
But the answer choice is not.
So if it come a question like this, do you write the answer down or what? You think?
Oh, no, that wouldn't happen on an actual test. What they'll do is they'll have these tests given, people look them over, and after they've come out, they'll scratch a few questions that either don't work very well, and they won't release them to the question pool. So you won't get this question in the question pool. That won't happen. You won't have something like this happen. We also, the way we'll check over questions too. We make our test booklets. Which of the following is a good way to judge whether your uplink power is neither too low nor too high? You want to answer C, your signal strength on the download should be about the same as the beacon. You don't want to overwhelm space stations. You don't want to transmit too much power to them. It can overwhelm their receiver, and then it takes them a while to recover. What is the impact of using too much effective radiated power on a satellite? You can answer, it's answer B, blocking access to other users. So you don't want to overwhelm the receiver. What is meant by the statement, the satellite is operating in UV? So UV, answer B, satellite uplink is on UHF, or 70 centimeters, and V, which is on 2 meters in the VHF band. So it's always uplink, downlink, 70 centimeters is a UHF frequency, 2 meters is a VHF frequency.
Will it always be 70 and 2, or will it just be some U frequency?
For ham
and some
purposes, it'll most likely be that. The ISS, I think, uses a VU just to mess with us, but every other thing uses UV. Digital modes. Hopefully we can get through at least about 5 or 6 of these slides. We're at slide 203. I wanted to get about 215. What code is used when sending CW and amateur bands? International Morse. Which of the following VHF, UHF frequency ranges are limited to CW only? So it's going to pull out there. We can first narrow a question down here. I can tell you that 2 of those, making 3 of those questions are incorrect because, oh, and I said that's like VHF, UHF. Tell you, generally speaking, if you were to look at your band plan, which you don't right now, but you would take the bottom end of a frequency range tends to be, the lower end of the frequency tends to be where the CW is. So I believe by looking at this that it's answer A. I may be incorrect. Yes. It's 50 megahertz. So those are the bottom of those bands. And I didn't know that CW was on that portion of the VHF only. So that's how I know that. That's a memorization question. What is an electronic keyer? To answer C, a device that assists in manually sending Morse code to make sure that your dits and your DAWs, your longs and your shorts and your longs are the same and they are spaced out properly. How might a computer be used as part of an amateur station? Oh man, computers, an amateur station. It does all of these things and much more, and half the time your radio is a computer. So I was hoping they were going to take that question out, or at least say radios, computers. When we get into the software-defined radio era of time, it's often very useful to have your radio and your computer be the same thing. How is a computer sound card used when conducting digital communications? Answer C, the sound card provides audio to a radio's microphone input and converts received audio to a digital form. It works, not necessarily the best way of doing things, but it's the way we've been doing digital modes and ham radio, especially on the HF side of things. Which of the following connections might be used between a voice transceiver and a computer for digital operation? To answer C, receive audio, transmit audio, and push to talk. So your computer needs to be able to control those things. Which computer sound card port is connected to the transceiver's headphone or speaker output for operating digital modes? It's the microphone or input lines you want to hear. If you want to hear on your computer, you hook up your audio out to your microphone. Which of the following connections might be used between a voice transceiver and a computer for digital operations? Answer D, all of these are correct. 802.11 Wi-Fi. packet radio J265. What is FTA? Ooh, that's a cool new question. I approve. So FTA is the new stuff for narrowband weak signal propagation. We love ourselves some FTA in our radio club. We do it a lot. It uses 15-second intervals to transmit and receive. So you have to have all your clocks timed out so they're correct. So everyone's clocks are synced. Use the computer to do that. And it goes in bursts of either odd or even. So you'll listen for 15 seconds and you'll transmit for 15 seconds and send you little pieces of data. And the usability of this thing is really cool. You can listen there for however long you want to. Someone's calling CQ, and you just double click on it, and your radio does all the transmitting, replies to them, and you have a conversation for about a minute. And you can figure out where they're located, how they received you. It's incredible. I think with that, I'm going to quickly, before you guys head out, see if I can pull up the FT8. They've got propagation maps. I think it's pretty cool to look at. So I'm going to end the stream here and I'll pull that up for you guys. So we're in slide 211.